All right, everybody. Hope you're having a good day. Wish you were here, but since you're not, we'll just have to do some math this way. So we're in our notes. You are on page 44, and we are ready to do problem 6B. These are a little bit thought-provoking, a little bit puzzly type. So let's look at what we've got going on here. Our job is to find the secant and the tangent. That's what we are looking for. The given that we have is that the sine is 1/5 and the cosine is negative. Less than 0 means the cosine is negative. Now, up to this point, when we did a problem and we had the sine is 1/5, we would draw this picture, opposite over hypotenuse. We would do the Pythagorean theorem, 1 squared plus b squared is 5 squared, and come out with a b value, which in this case does reduce to √6. And then based on that, we would fill in everything else. We did several problems like that. Now, what's different is, if I said to you, look at this triangle, which has a sine of 1/5, and I said, okay, what's the cosine? You would say 2√6/5. That's the cosine. And that's perfect, except it's not negative. And according to the directions, the cosine has to be negative. So that means our picture needs to be in a different quadrant. And it needs to be in a quadrant where the adjacent side is negative. So guys, does it make sense to you that instead of looking at that triangle, maybe I should be looking at this one? Because the sine is still positive 1/5, but now the adjacent side would be negative 2√6. The Pythagorean theorem doesn't change, so it's still 2√6, and now it would be negative, which is exactly what the problem said. So we needed our sine to stay positive, which it is, but we needed our cosine to be negative. So the blue triangle, I hope you can see the colors, this triangle right here is the answer, well, is the picture for the problem. So now I can answer the question using my blue triangle, this one, using this triangle right here. What is the secant? Well, the secant is the reciprocal of the cosine. So it will be hypotenuse over adjacent. 5 over negative 2√6. Hypotenuse over adjacent. Now, I'm going to get rid of that radical, so I'm going to multiply by the √6. So on top, I have 5√6. Now remember, √6 times √6 is 6, times 2 is negative 12. So there's your secant. Now tangent, same thing's going to happen with the tangent. We're going to put opposite over adjacent. We're going to have to get rid of that radical. So we have √6 on top. This makes 6 times 2 makes negative 12. And there is your tangent. Now I know that problem is a lot. So if you got lost in there somewhere, hit rewind and go through that again. Those steps are important. They're not hard. There's just a lot to think about. So quick recap. They told me the sign was a positive 1/5. So I went ahead and drew it like I always draw it. There it is. I did my Pythagorean theorem and found out that the other side was 2√6. Now that was a problem because the cosine of this black triangle is a positive number. And according to my directions, the cosine has to be negative. So that means I had to move my triangle. So I moved it over here so that the 2√6 would be negative. The sine is still positive. The cosine is negative, so that's the triangle I wanted. Now some of you might be thinking, Mrs. Ford, why didn't you move it into quadrant 3? Well, I can't move it into quadrant 3 because in quadrant 3, the sign would be negative. It would be negative 1/5. I need it to be positive 1/5. How about quadrant 4? Same thing. I can draw a triangle in quadrant 4, but it will have a negative sign, and I need it to have a positive sign. So my only choice, I tried this one first, it didn't work. So then I moved over here and it worked. This quadrant doesn't and this quadrant doesn't. These two don't. The only quadrant that works is quadrant 2. Nothing is memorized there. I just tried it. I just drew it, worked my way around, and this one actually worked, so I went ahead and used it. All right, now that problem is important because this last section of problems, I think this is the last section in 4.3, this last section of problems says, find all of the angles, and that's the key. Find all of the angles that satisfy this equation. So in other words, find all of the angles, butterfly bow tie, that adjacent is negative and hypotenuse is positive. Now remember, hypotenuse is always going to be positive. Hypotenuse is always positive, so that works everywhere. But where will the adjacent side be negative? Now remember, this is your angle right here. So isn't this the adjacent side? Well, on this side, the adjacent side would not be negative. But what about over here? Yeah. So you're going to have an angle in quadrant 2 that has a hypotenuse is 2 and the adjacent side's -1. And you're also going to have one in quadrant 3 where the adjacent side is -1 and the hypotenuse is 2. You have both of those. Both of those are quadrants where the cosine is negative. Now, you should recognize this picture. If that's a 1 and that's a 2, that's a √3, and this is a 60. This is exactly the same triangle, it's just in a different quadrant. So when you do these problems where you have multiple triangles, the angle will always be the same. It'll be in a different quadrant, but it's 60 here and it's 60 here. Now, here is the new part. 60 is not the answer. Remember, our framework is 0, 90, 180, 270, 360. This, my friends, is the answer. You must start measuring your angle at 0. So you're going to go up past 90 until you get to here. That blue thing is the answer to the question. Now, tell me this. How how big is that blue angle? Now remember, if you went all the way to here, it would be 180. But I didn't go that far. I stopped here. So if I stopped 60 degrees before I got to 180, then isn't this angle 120 degrees? Yeah, it is. It's 120 degrees. Now what about this one? Start here, work your way all the way around till you get to your angle line, your diagonal line. Now how big is that one? Well, this one went past 180. This one went 60 degrees past 180. So that angle is 240 degrees. So the answers to that problem are 120 and 240 in degrees. We're going to have to change those to radians in a minute, but those are degrees. The question says answer in degrees and radians. So I've got my degree answers. My reference angles are 60. This one is 60 less than 180, and this one is 60 more than 180. Okay, so now we got to put those into radians. How do we do that? You know how to do that. Let's do 120 first. To change 120 into radians, we're going to do pi is to 180 as something is to 120. So x equals 120 pi over 180 if I just bring the 120 over. Cancel the zeros. 12 over 18 divisible by 6, so 2 pi over 3. So 120 degrees is 2 pi over 3 radians. Now I'm going to do the same thing, the exact same thing, with 240. So pi is to 180, as something is to 240. I'll bring the 240 over, cancel the zeros. Now I have 24 over 18, which again divides by 6, so that will be 4 pi over 3. So 240 degrees is the same as 4 pi over 3. Wow, all that is one problem. All right, next one, sine theta equals root 3 over 2. Now, again, we want all of the angles. So I think, at least I hope, what you're thinking is, hey, I could draw my normal triangle right here in quadrant 1. I could say opposite is root 3 and hypotenuse is 2, and that'll work. And you are absolutely right. But there's another one that will work. Where else? Think about your other options. Think about all of your other options. Where else would opposite be positive and hypotenuse be positive? Well, hypotenuse is always positive, so we really don't have to worry about that one. But where else is the opposite positive? It's positive right here. Where else is opposite positive? Would you agree right here? That that's root 3 over 2 in that quadrant? Indeed. And as luck would have it, what angle is across from the root 3? 60. So we got the same angle. Now, your answer must be measured from here. This is where we start. So start right here and go up until you hit the diagonal line. Well, that's an easy one because that is 60. So theta is 60 degrees. This one's not so easy. You got to start here and go around till you hit your angle line. Remembering that this is 180, but I stopped here, which is 60 before I got to 180. So that angle is 120 again. So your two answers in degrees are 60 and 120. Now put them in radians. Well, this one I just did, so I know this one is 2 pi over 3 because I just did it. And this one, if I'm really thinking, I don't even need to mess with it because 60 is a third of 180. Now, I could do that. If you want to do this with 60, go right ahead. It's going to reduce to 1/3 pi. 60 is 1/3 of 180. So it's 1/3 of pi, pi over 3. All righty. I know it's a lot, but the beauty of the video is you can stop me, rewind me, and start me back up. You can also just skip ahead if you're getting it. All right, tan theta equals 1. So think about what that means, just in terms of our regular basic picture. Opposite over adjacent is 1. That triangle makes sense. That triangle works. The tangent is opposite over adjacent. That's 1 over 1. Done. Now, here's the tricky part. Where else could, well, I already drew that one. Where else could I have a triangle where opposite and adjacent, opposite over adjacent, turn out to be 1? Now this is a little bit tricky because certainly they can both be positive, but couldn't they also both be negative? Wouldn't that give me a tangent value of 1 if they were both negative? Well, where does that happen? In our situation, where would the triangle be where opposite and adjacent were both negative? Wouldn't that be right here? Negative, negative. Now, these two angles are the same size. They always match. When you're doing two triangles for the same picture, the angles are always the same. So 1, 1, root 2, this is a 45-degree angle right here. This is a 45-degree angle right here. Now you've got a good picture drawn. Now you need your angles, your answers. So here's the first answer. Remember, we start here where my hand is, that's 0, and go up and around till we hit a diagonal line. So right there's our diagonal line. So that angle is 45 degrees. Same thing here. Start here, up and around till I hit the diagonal line. Now how big is that angle? That angle is a full 180 plus 45 more. So that's going to be 225. Now some of you are probably thinking, Ms. Ford, how do you know it's not somewhere else? Well, think about it. Think about if you put it down here, for example. This would be 1 and this would be negative 1. So when I did the tangent, wouldn't I get negative 1 instead of positive 1? I'm supposed to be getting positive 1. So this won't work. You can't have one negative and one positive. They have to either both be positive or both be negative if we're going to end up with a 1. So my angles are 45 and 225. Now I need to change those into degrees, or excuse me, into radians. So I don't know, we've done quite a few of these. 45 is a fourth of 180. So this is pi over 4. Now if that bothers you, pi over 180 equals x over 45. So x equals 45 pi over 180 if I multiply this over. These are both divisible by 9, so that's 5 pi over 20. Those are both divisible by 5, and that's how I get pi over 4. We've done enough, and we're going to do more. It's okay if you're starting to get the feeling that pi over 3 is 60, pi over 6 is 30, and pi over 4 is 45. Those are the very common ones, 30, 60, and 45. All right, what about 225? Well, 225, we can do the same thing with that. Pi over 180 equals x over 225. So I'm going to solve this proportion. I'm going to reduce the fraction. Now, I don't know what you think of when you look at this. I think 5. So 5 goes into 225. $45 times. And 5 goes into 180 36 times. Now 9 goes into both of those. So that's going to be 5 pi over 4. So this one is 5 pi over 4. Don't want to confuse the issue, but if you look back at the problems we've done, if your reference angle is 60, if our triangles had 60s here, our answers were some pi's over 3, because 60 is pi over 3. If our angle is 45 degrees, then our radians are going to be something over 4 all the time. You don't have to memorize that. It happens, it's true, but you can always work it out, just like this. All right, one more to go. Sine theta equals 1. This one is tricky. And the reason it's tricky is because it would require, you think about what sine is, it would require the opposite and the hypotenuse to be the same. Can you make a triangle, a right triangle, where the hypotenuse is the same as the side? No. The hypotenuse is always longer. So if you're thinking, yeah, that's one of our special triangles. No, it's not. Our special triangle has sides that are 1 and the hypotenuse is root 2. The hypotenuse cannot ever match a side. So what does that mean? That means that no triangle is possible. Well, shoot. What do I do in trigonometry when a triangle isn't possible? I draw a circle. And I'm going to let the radius of that circle be 1. Just like I did yesterday, I don't know. I'm gonna let the radius be 1. And if the radius of the circle is 1, then this is 1, comma 0. This is 0, comma 1, negative 1, comma 0, and 0, negative 1. I'm not memorizing those, that's just natural plotting points. Here's the origin. Up 1, left 1, down 1, right 1. If I'm in the circle, then I gotta use my circular definitions on my purple sheet. So according to the purple sheet, the sine of an angle is y over r. Now, this part is going to be 1 always. I set it up that way, so the radius is 1. Now, I need y to also be 1, right? I need my sine to be 1 over 1. So sine is y over r, so that has to be 1 over 1. Well, this is going to be 1, because that's how I drew my circle. What about this? Where on that circle is the y coordinate 1? There's only one place. The y coordinate's 1 right here. X, y. That's the only place that the y coordinate's 1. So the answer, the angle that you are looking for, start here, go to your angle, which in this case is right here. How big is that angle? That angle right there. That's 90 degrees. And what is 90 degrees in terms of radians? Well, you can work it out with your proportion, or you can just remember that 90 is half of 180, so this is going to be half of pi. This is for why did you draw a circle for that problem? All the other problems we did triangles for. Why did you do a circle for this one? Because I couldn't draw a triangle. If you can't draw a triangle, then you're going to have to draw a circle. And the minute you draw a circle, you are using your circular definitions. Sine is y over r. So I simply looked around my circle. Where is y1? R is always 1. So I had to find where y was 1, and that was right there. Okay? And that takes care of 4.3. So that homework will be due on Friday. Okay? And these notes need to be completed by the time we have class again. So I don't know when that is, but whenever we have class again, these notes have to be completed. Now, we are going to forge ahead and do a little bit of graphing. Not a whole lot. I don't want this video to get unbearably long, but we do need to keep plowing through. Chapter 4 is huge. So here we go. So we're going to do a little bit of graphing. So 4.4, the first 2 graphs are just the straight sine and cosine. This is kind of review from your BFFs. When we did this back in BFF time, you drew a curve, started at the origin, went up a hill, made a valley, and stopped. Now, maybe you've forgotten that. I don't know. We said the sine goes through the origin, so there it is. It does go back and forth. You only need to draw this much. You can certainly always draw extra, but when you draw a sine, I expect to see 1 hill and 1 valley. Okay, there's lots of hills and valleys. Normally we draw this one and this one. Now, the extra that I'm adding at this point is some labels. 1, -1. So the top of the hill is 1, the bottom of the valleys is -1. And then these labels, we're going to label here, which is the top of the hill. We're going to label here where it crosses. We're going to label the bottom of the valley, and we're going to label where it ends. Those 4 points are actually the quadrants of a circle. If you want all around your 4 triangles, butterfly bow tie, each of these sections represents a triangle, one of those quadrants. And the labels, the end label is 2 pi. Now, why is it 2 pi? Because all the way around the circle is 360, and 360s are 2 pi. So this represents all the way around the circle, all 4 quadrants. If that's 2 pi, then right here in the middle, obviously will be 1 pi. And then right here in the middle of these will be half a pi. You can write 1/2 pi if you want. We normally just write pi over 2, but it's up to you. And then this is 1 and 2. So right in the middle of that would be 1½ pi. Now we never write that. It is 1½ but we write it as 3 pi over 2, 3 halves, 1½ 3 halves. That is your sign picture. So as you look down through these problems, you'll notice that we're making all kinds of changes to our sine curve. Some of the problems are sines, some are cosines, but we're sticking extra numbers in. This is what you need to start with. The height of the hills, which obviously is the same as the depth of the valley, is called the amplitude. The amplitude of the curve. It's the height of the waves. So the amplitude of the regular sine, this is your regular sine function. This is what we memorize. The regular sine function, the amplitude is 1. On this exact picture is on the back of your purple sheet. The distance from start to finish is called the period. Okay, so amplitude is the height of the wave. How high is this wave? It's 1. Period is horizontal. Distance from here to here. And that is 2 pi. When we start putting numbers into our equation, these things are going to change. Because you remember that numbers in the equation stretch it this way, that'll be an amplitude change, and stretch it this way, that'll be a period change. But before we do any of that, we've got to get our cosine graphed. So again, I don't know if you remember your BFFs, but the cosine picture started up here and did this. Now, it kept going, so I don't want you to get confused. It kept going. But the only required chunk is this blue piece right here. It consists of 1 valley and 1 hill. But because of the way it's positioned, the hill has been split. Can you see that? You got half a hill, your valley, the other half of the hill. This is 1 period. The labels are the same as for the sign. So 1 and -1. So my amplitude is 1. I'm going to abbreviate amp. Amplitude is 1. Height, 1. And my period is also 2 pi. This label right here, where we end here, of the blue, the end of the blue, is 2 pi. Right in the middle, which is the bottom of the valley, is pi. This is pi over 2, and this is 3 pi over 2. That is your cosine curve, and that's what you gotta know. Because if you don't know this, then there's no way you can handle it when we stick a bunch of numbers in. All right? And I promise I'm going to do only 2, and then I'm going to stop. Okay? I'm going to do 2 problems. I'm going to do C and D, and then I'm going to stop. Now, I wish I hadn't made these quite so big. So I'm going to go ahead and I'm going to draw my standard sine curve up here at the top of the page, so I have it to refer to. And then my standard cosine curve up here at the top of the page, so I have it to refer to. All right, because now I'm going to start putting some numbers into the problem. So, first one is letter C, 2 sine x. So first of all, it's a sine, so it's going to have this shape. And there's a 2 out in front. Okay, who remembers from way back in chapter 1? Who remembers what putting a number in front of a function does? I know somebody remembers, I wish you were here. Putting a number in front of the function multiplies the height. So what that means is I have my sine curve that normally goes up to 1 and down to -1. Normally the height is 1, but now I've put a 2 out there. So now my height is going to be 2. A number in front multiplies the height of your waves. Now, does a number in front have anything to do with the horizontal? Nope. So these labels haven't changed. Pi over 2, pi, 3 pi over 2, 2 pi. Those are my labels. They have not changed. The amplitude of this picture, we need to get in the habit of writing this down each time. The amplitude of this picture is now 2. Amplitude is height. The height is now 2. What about period? Well, the period hasn't changed. Period is here to here, which is 2 pi. We have not done anything, we haven't put any numbers in the problem to change that. The only thing we did was put a number out in front, which makes the thing twice as tall. Think about it, I don't know if you do physics, if you know sound waves. If you turn up the volume on your radio or something, you're turning up the amplitude, amplifier, you're making it louder, those waves are getting taller. All right, last one. Y equals -3 cosine x. Now, 2 things have happened. First of all, it's a cosine, so it looks like that. But who remembers what a negative does? A negative out front. A negative out in front turns your picture upside down. It reflects across the x-axis. That's the mathematical way of saying it. but basically it's going to turn me upside down. So instead of having that shape, it's going to have this shape. Upside down. Now normally, the height of the cosine is going to go up 1 and down 1. Not this time. What does this number out in front do? The number out in front multiplies the height. So now these things are going up 3 and down -3. So it's upside down and 3 times as tall. Now, did I do anything to change these? Nope. Didn't do anything to change those. What's my amplitude? Be careful, it's +3. Amplitude is always positive. Amplitude is height. So the amplitude is 3. I know it's a negative, but all the negative does is turn upside down. Amplitude is positive. So amplitude's 3, period is still 2 pi. Next time we're together, we'll change the period. But for now, we have learned, reviewed, talked about how we change amplitude. I lost my little pin thing. We changed amplitude and direction. We turned it upside down. All right, thanks a lot, guys. That takes care of that. I'll see you next time. And 4-3 homework is due Wednesday. Have a great day. No, due Friday. 4-3 homework is due Friday. Thanks.